everyone. Today we're going to talk about equilibrium. We're going to start talking about equilibrium. And so this is kind of a little introduction into what equilibrium is and the equilibrium constant. And we'll also be talking about the reaction quotient today. First and foremost, let's look at this graph together. And I want you in your head, before I give you the answers, obviously, uh, try to determine which things are the reactants here and which things are the products. Notice how on the x-axis I have time, so as time goes on, and then the y-axis here is the concentration. That's what those brackets mean. It means concentration. So like this line right here is what's happening to the concentration of nitrogen dioxide. This line right here is what's happening to the concentration of carbon monoxide, and this right here is what's happening to the concentration of nitrogen monoxide and carbon dioxide. This isn't them added together, they just both happen to be the same concentration. So think about it, maybe pause this video if you need to think about it a little bit more. Which ones are the reactants? Which ones are the products? So these two things are the reactants, and these two things are the products. Now, the way we can tell this from this graph is that at time t equals 0, we have some of these reactants, but we don't have any product left yet. Because as the reaction goes on, we're going to decrease the reactants and we're going to increase the product. So here we can see this will be our reaction. Here we have nitrogen dioxide plus carbon monoxide react to form nitrogen monoxide and carbon dioxide. This is already balanced. We're good there. My next question for you is, why do you think the reactants never run out? We kind of get this plateau of concentration. So we don't go down to 0 for our reactant concentration. We kind of hit the stability line. Now, the reason for this is that some chemical reactions, not all, but some chemical reactions are reversible. And so once that nitrogen monoxide and carbon dioxide, our two products, form, some of those things will react together and go back to form nitrogen dioxide and carbon monoxide, our reactants. So this is called a reversible reaction, and we represent these with a double-sided arrow. It looks like this. So this means that this reaction can go forward. It can also go backward. So how do we establish equilibrium? Well, what happens here is that at the very beginning of the reaction, we have all reactants and no products present. So this is like our time t equals 0 on our graph. At the beginning of this reaction, the rate of the forward reaction is very fast because, again, we have all reactants, no products. We want to form those products. The rate of the reverse reaction at the beginning is 0 because I don't have any products to react together yet. As the reaction proceeds, during that reaction, the reactants are going to decrease and the products are increasing. Here, the rate of the forward reaction is going to be slowing down and the rate of the reverse reaction is going to be speeding up. Then at equilibrium, this point that we establish, the concentrations of the products and reactants do not change. So this is like our plateau here. Our concentrations are going to be remaining constant. However, they're not the same, and we'll talk about that in a bit. But those concentrations are constant, they're not changing, and that means that the rate of the forward and reverse reactions are going to be equal. So you're forming as much product as you are reactant. So the forward and reverse reaction rates are equal. Now, there's some common misconceptions here with this nomenclature. And the misconceptions here that a lot of people kind of get very confused about. The first one is that the concentrations of the reactants and products are constant. They are not equal. So look at this graph again that I showed you before. Notice how the concentration of nitrogen dioxide is the highest concentration. The next lowest concentration is carbon monoxide, and then we have the lowest concentration here are the concentrations of our nitrogen monoxide and carbon dioxide. So notice how these concentrations are different at equilibrium. However, they are all constant. So the concentrations of the individual species are not changing, but the concentrations themselves of the individual species are not the same as all of the other ones. Okay, so that's very important. The second misconception here is that once you reach equilibrium, the reaction just stops. That's not true. Once you reach equilibrium, the reaction does not stop. It keeps going, but the rates of the forward and reverse reactions are equal. So that's why we don't have a net like increase or decrease in reactants or products. They're going to be the same concentrations and they remain the same constant concentrations because the rates of the forward and reverse reactions are equal. And then again, just to reiterate, those concentrations themselves are not equal. It's the rate of the forward and reverse reactions that are equal. Now, let's talk about what the equilibrium constant is. So, the equilibrium constant is a number that indicates the ratio of products to reactants at equilibrium for a given reaction and temperature and pressure, I should say. The equilibrium constant for a certain reaction can change if temperature and or pressure changes, but we'll talk about that more when we talk about Le Chatelier's principle later this unit. The equilibrium constant is denoted by the letter capital K. And we don't have units here. It's just a number. Okay. Because it's a ratio, what we do here is to find it, it's a fraction. And the fraction looks like this. It's the concentration of the products over the concentration of reactants. So just looking at this number here, we can see that at equilibrium, if we have a very high concentration of products versus reactants, that means that K will be high. At equilibrium, if we have a higher concentration of reactants compared to products, then K will be low. Now, K can't be negative because we're talking about concentrations here, but it can be less than 1. So it can be like 0.13 or something like that. It can also be in the thousands. So there's a great range of K values that can, be allowed, but it cannot be negative. So if I had a reaction that looks like this, it looks weird because they're just kind of placeholders. The capital letters A, B, C, D, those are like the chemical formulas. So the things that are actually reacting. And then my lowercase letters here are coefficients. So little a is how much of big A I have, if that makes sense. Now, the reason I give you this is that when we're solving for K, again, it's concentration of products over concentration of reactants, we actually have to raise the concentration to the coefficient power. So it looks something like this. Again, C and D are my products, so those go on the top. A and B are my reactants, so those go on the bottom. Notice how I'm raising the concentration of C to that power of the coefficient. Again, raising the concentration of D to the power of that coefficient. Raising the concentration of A to the power of that coefficient, and then raising the concentration of B to the power of the coefficient. Also notice how we're not adding these together, okay? We're multiplying. So you have multiplying C and D together, multiplying A and B together, and then you're dividing, okay? So that's how you would solve for K. So like I said, coefficients become exponents, and then those brackets mean concentration or molarity at equilibrium. Now, substances that are pure solids or liquids are not going to go in this K expression, and that's because they don't have a concentration, right? Concentration only applies to gases because that concentration can be changed depending on, the density of the gas or the volume or the pressure. However, like a liquid or a solid, we can't change those concentrations. We can change concentrations of aqueous substances in liquid. So when something has an AQ next to it, then yes, we can get a concentration. So we're not going to put pure solids or liquids into this equilibrium expression. So we only include things that have an AQ or aqueous substances or a G next to them. Like I said, these are the only things that have a concentration. So we also can have what's called a partial pressure equilibrium. So if we don't have molarity or concentration, but we have like partial pressures of gases, those can also go into our equilibrium constant equation. So again, this is for gases only because gases are the only things that have partial pressures. And what we do is we just replace molarities or concentrations in our equilibrium expression with partial pressures. So an example here would be a container is filled with a mix of PCl3 and Cl2. At equilibrium, the partial pressures are 0.124 atmospheres for PCl3, phosphorus trichloride, 0.157 atmospheres for chlorine gas, and then our 0.13 atmospheres for the product, which is our PCl5, phosphorus pentachloride. Now we're going to see what the value of K is, assuming the temperature is constant. Here is our equation here. It is balanced, so it's a 1:1:1 ratio. And when we're solving for K, remember it's concentration of products over concentration of reactants. So here we get the concentration of our PCl5 over the concentration of PCl3 times the concentration of PCl2. Again, because these are gases, instead of concentrations, I can use atmospheres. Doesn't mean it has to be pressure when we're talking about gases. You can also have a concentration of a gas, which is what I will usually give you, but you can use as partial pressure equilibrium. I don't have any exponents in my equilibrium expression here because there's no coefficients, so the exponents are all 1. Plugging in my numbers here, I get that 0.13 on the top, and then my pressure for PCl3 was 0.124 atmospheres, and then my pressure for chlorine gas was 0.157. Doing the math here, we get 6.67 for our equilibrium constant. Notice how I didn't write my units in my K expression because K is unitless. So the units are not going to work out. If we kept the units here, you would get, 1 over atmospheres, which it's going to be different for any equation because we're going to have a different number of products and reactants in the equation. We're going to have maybe different exponents because of the coefficient. So the units for K, if there were units and you tried to cancel them out and things like that, they would never work out the same from reaction to reaction. So it's just unitless. It's just a number. All right. Okay. Now, last thing we need to talk about here is the reaction quotient. Now, the reaction quotient is the ratio of products to reactants using the same equation, so same equation for K, at any given time, though. So K is only at equilibrium. Q, our reaction quotient, is at any time. So again, K is only at equilibrium. Q is at any time. What we do here is we plug initial values or concentrations into our equilibrium expression, and we use that to determine whether or not a reaction is at equilibrium. For some reason, this tends to be very confusing for a lot of people, but it's really just the same equation. And all I will say is is this reaction at equilibrium? And if Q and K are not the same number, you just say no, and that's it. So if Q equals K, the reaction is at equilibrium. If Q is not equal to K, the reaction is not at equilibrium. So let's do a couple examples here. We have this reaction here. 2 nitrogen dioxides react to form dinitrogen tetroxide. Initially, 2.5 moles of nitrogen dioxide gas and 4.5 moles of dinitrogen tetroxide is placed in a 1 liter reaction container. I want the equilibrium expression, determine the value of Q, and is the system at equilibrium. Now, whenever you're given information like this, 2.5 moles and 4.5 moles in a 1 liter reaction container, remember molarity or concentration is moles over liters. So this is just 2.5 moles over 1 liter, which is 2.5 molar. All right, so I'm giving you concentration here. I will not always have a 1 liter reaction container, so you might have to find molarity first before you would plug it into K, or later ICE tables when we talk about those, but I'll talk about those later this unit. So we have 2.5 molar concentration of nitrogen dioxide and a 4.5 molar concentration of dinitrogen tetroxide. So writing the equilibrium expression, remember K is products over reactants. We get our product, concentration of our product, over the concentration of our reactant squared, because again, there's a 2 coefficient in front of that NO2. So that's why it's squared. Now, we use this same expression to plug in the numbers that we have. So I have Q is equal to the concentration of my product over the concentration of my reactant squared. And then solving this, we get 0.72. I give you the equilibrium constant up here is 1.5. So we could see that 0.72 is not equal to 1.5. So my answer for C is no, the system's not at equilibrium because Q does not equal K. And that's as simple as that. All right, let's do one more example. So I'm given a reaction. I have some concentrations over here on the left-hand side, and I'm given my value of K, which is 0.345. So plugging this stuff into my equation, again, products over reactants. In this case, I have one product, but there is a coefficient of 2 in front, so I'm going to have to square that concentration, that 2.7. I'll have to square it on the numerator. And then I have my concentration of SO2, which is 0.25. I'm going to have to square that also because of that coefficient. And then my concentration of 0.83. So that goes into my equation here. So plugging in my numbers, I end up getting 140.5 for Q. Way higher than my equilibrium constant K. So again, because Q does not equal K, I am not at equilibrium. My system's not at equilibrium. Now, one more thing I want you guys to think about is what this number means, right? Well, as we approach equilibrium, this reaction quotient number, 140.5, it's going to decrease because I'm eventually going to end up at equilibrium. I'm going to end up at an equilibrium constant of 0.345. So in order for that thing to decrease, I need the concentrations of my reactants to increase and the concentration of my product to decrease. Because if I increase the denominator and decrease the numerator, my Q will decrease. All right. So what we would say here is that the reverse reaction, going from products to reactants, the reverse reaction will be the dominant reaction as this reaction proceeds and goes toward equilibrium. So my reverse reaction is speeding up. My forward reaction is slowing down as we approach equilibrium. So that's something else to think about. Which direction will this reaction proceed in order to reach K? All right, so that is an introduction to equilibrium. Again, we talked about equilibrium concentrations, what those mean, misconceptions, and we talked about the equilibrium constant and the reaction quotient. Let me know if you have any questions, and I will see you all in class.